Alright, so in doing linear regressions, we will start out with any two data sets that are not known to have any functional relationship at all. So for example, let's have a look into my data that I have prepared in a Microsoft Excel table. So this data set here in my highlighted area, right from the moment we recorded the data, or right from the moment the data was recorded, then everything we know is that these are two different data sets. And here in this example, I'm just calling this column here is to represent the data X, and this other column is to represent the data Y. And all we know is that every value X and Y here is being recorded as a pair, being observed as a pair. So when X, in the data X, when the value is 5, correspondingly the Y value is 0.45. 6 is for X, then the corresponding Y value is 0.62. And as I said, we don't really know if the two data here are having any kind of functional relationship at all. So in that way, we can sort out one column. So say, for example, I already sorted out my column X right here in ascending order or descending order, however you want to put it. But once you sorted one column, then the values of the other column have to fall out accordingly to how these values are in the X column are being arranged, because these values, once again, they are intended to be paired data. So they exist permanently as a pair, as a partner of two values. And so to know that we have a data, two different data here being paired up, then we can put up a, let's say in a graphing space right here, we can plot those pairs of value into what's so-called scatterplot. So the scatterplot here, so what we see here on the screen is called a scatterplot. And so back to the screen here, back to my graphing space here, the scatterplot simply just each point here on the scatterplot simply represent one point of data. So we traditionally put X value on the horizontal axis, the Y value on the vertical axis. And so let me show the point label so that you can understand a little more easily. So first point, for example, came out from X value being 5, Y value being 0.45. And next value here is being 6 for X and 0.62 for Y. And so we put these points, and each of these points exactly reflect our pair of data. And for now, as I already said a couple of times already, that we don't know if these two data, so we don't know if each point here in our scatter plot is having, or all these points here on our scatter plot are having any functional relationship. So in that way, the attempts to look for a curve or a graph that contains through all these points is going to be nearly impossible. So the idea now is that instead of looking for a graph that connects all these points, that contains all these points, we are looking for what's so-called a regression line. So let me quickly put up a regression line right here. And of course, we're just starting, so there will be a lot of questions about how did I come up with all this regression line right here. It will come in the following example as we start doing the work right here. But so this line here is called the regression line. And all it does is that it makes the best distance. And this line here out there a lot of time is also being referred as the best fit line. And so the line that you're seeing right there on the graphing space is called the best fit line. And sometimes people also refer to that as the regression line. And so, and this line here is a close enough substitute as if we were attempting to look for the graph that contain all these points, and instead of doing that, we substitute that with one line right here, making the best distance, the least distance from every point right here. And then this line right here is, we're going to be using this best fit line here as a way to predict other values, that because you can see that our data, and any data is always limited. The data we observe will always be limited. So we want to use this best fit line to aim at that purpose, to predict those values that are outside of the data. So in my other videos outside of this lesson, I'm going to be showing examples how we can use technologies, different kinds of technology to help us calculate the best fit line and put it on the graph. So now, once we have learned that technology of some kind can help us quickly and effectively find the correlation coefficient of a data, or as well as the slope and y-intercept of the best fit line equation, then back to this data that we started out since the beginning of our lecture here, then this data, according to calculation, we have the correlation coefficient is calculated right here, being 0.844277, so on and so on. Normally, for my lecture in class, then I use about 5 decimal places here, but it's pretty much depending on every different problem. And so, once again, you've seen that through the technology example, but in a TI calculator, then this is the slope of your best fit line equation, and this is your y-intercept of the best fit line equation. And so when it comes to writing down the actual best fit line equation on paper or on printout papers, agreeing your equation is simply y equals, I'm going to be using 4 decimal places for any of my parameter here, 0.033 for x plus 0.3511. But this is a requirement that has been required by all statisticians out there. But anytime we write the best fit line equation, make sure we put hats over our variables. And I can guarantee that no technologies will know how to do this. Only for us right here, anytime that we are writing down the actual best fit line equation, and make sure you put the hats down. The reason for this is that the only purpose of this best fit line equation is to come up with prediction value. And so, once again, let's look back to my data here. But values that's already been recorded on the data table is considered as observed values. So these are the observed value. But then sometime we are going to be using the equation to find out values that are off the table. And so the values that being calculated through the equation here, the best fit line equation, are only considered as predicted values. And so my bottom line here is that the reason we're using hats on top of our variables here is because the equation of the best fit line only gives a prediction of x or y values. And that's the reason why anytime it comes down to writing the best fit line equation on paper, we need to put hats over our variables. And then let's now understand a little further about our correlation coefficient here. But so once again, the technology calculated for us that our data here, in the data we are using in this lecture, is having correlation coefficient equals to value 0.84425, and allow me to use 5 decimal places for this value. But what we notice here is that the correlation coefficient value is a positive number. And so how is this connected with the graph and with the scatter plot that we have seen previously? So allow me to bring up the scatter plot of this data over here. So here's our data once again, and the scatter plot is here. And also I'm still leaving that best fit line together with the scatter plot here. But so in the way how we're looking at scatter plot now, we, like I said again, we don't really need to have a functional graph or some kind of curve that contains all these points. But what we're looking at now is that the entire region that's made up of all these scatter points right here. So this entire region is called the scatter region. But in the end, if you're looking at the entire region, there are quite a few bouncing up and down, but the entire region in the end forms into a rising from the left to the right, a rising trend. And obviously, having the best fit line being displayed together here can make it clear that our best fit line is having a positive slope, and the line itself is rising from the left to the right. And that is, once again, back to my writing board here, that is how the correlation coefficient value being positive explains for that. And so it didn't happen in our example here, in our lecture example here, but there could be time out there that when you're looking at a scatter plot, and when your scatter plot forms into a scatter region that seems to be falling from the left to the right here. Normally I call it's a falling trend. And then even when you put up the best fit line right here, the line is also falling from the left to the right. This case right here is indicating, now of course we don't have any real data, but if once we calculated the correlation coefficient value, this correlation coefficient value of a scatter plot like this should be a negative value. And now think about the same data set here that we started out in the beginning of our lecture here, but now I'm going to actually change this entry here, the point 53 here. I am going to change that to become a point 65, and then this next entry here, I'm going to change that to a 0.7. We can think of this as a completely different example here. The data looks almost the same with the earlier one, except for these two entries. It's been updated, been changed to different values. But now let me bring up the scatter plot again, and you will understand. You will see the first change, what it does, changing this data. You will see how changing these two entries will cause some change to the scatter plot here. But so now, once we change these two entries, then here's what the scatter plots become. So there's still some best fit lines. Every scatter plot has a unique best fit line. And here, like I said, even though most of the data has been the same, but it's a completely new data. But now this data here, after the updates here, with a different best fit lines, but case all scatter points become closer to the best fit line. And the distance from every point here is smaller to the best fit line here. And I'm not saying that the best fit line is the same best fit line as of the earlier data. But now you can see that we having, in a daily language right here, in a daily term, it's a thinner bandwidth. And so the calculations of the R value this time, and you can see that it's also changed. I actually changed the data in my calculator here as well. But so once we calculated the correlation coefficient, we have a different correlation coefficient value as well. So you can see that the correlation coefficient this time in 5 decimals, it's 0.92300, or it's ridiculously just 0.923. It's still a positive, clearly, because the line was still rising up. But the way how I see that now is that this value is closer to +1. And so another thing to understand about correlation coefficient is that, first of all, calculated value for any correlation coefficient must only happen anywhere from -1 to 1. It's just the way it is. We are not really required to look at any formula, but the way how the formula sets up, and that runs into the being programmed into our technology right there. So the output turns out for correlation coefficient value will be anywhere inside of this interval from -1 to 1. And so now connecting with what we have seen just through the live example there is that now anytime that your scatter plots give a scatter region that's closely lined up into a line right there. And closely, I mean not perfectly on the line, but these points are all making a small distance from each point to the line. Then first of all, once again, the general understanding here is that the R value is closer to +1. But then in this particular new example, in this particular new data that we came up with, R equals 0.2300 over here compared to the version early before that, then you can say that this data fits the linear model better than the other data. And the other data, I meant the earlier data that we started out in our lecture there. And so, and some other times data can happen. In some other times data can happen as some scatter plots that form a falling trend, a falling bandwidth, and then there's another scatter plot also forming into a falling trend, but we have a thinner, points are more closely lined up on its best fit line compared to something like this. And so we already learned that this is when R is negative, but here furthermore in a case like this, R is closer to -1. And as far as comparing the two versions right here, then this data, similar to what we have seen in the quick example above, then this data compared to the other data fits the linear model better than the one on the left.